Hey folks, this next video is going to be dedicated to discussing ways in which information or data can be organized, namely in a frequency distribution. And there's different types of frequency distributions, and in particular we're going to talk about different types of graphs. And in the previous video I've shown you a bar chart and a histogram, but we're going to thoroughly go over those types of graphs now. So what is a frequency distribution? This is a graph or a table that will display how often, how frequently a particular value or category occurred in the data set. As you may remember, we've got categorical data and quantitative data. And if you want to make a graph that condenses and organizes categorical data, we usually do so in a type of bar graph or a bar chart, and we can use those terms interchangeably. So let's look at an example of a bar chart. I've got a fictitious data set in mind, and I'm going to lay down a set of axes. Okay, in this horizontal axis is where we usually name the variable of interest, and for my variable that I've got in mind, we saw it in a previous video. I'm going to call this teacher rating. So this is going to be a categorical variable, and I'm going to put some tick marks here and name them from worst to best. Unacceptable, hopefully that's enough, poor, fair, good, and excellent. Okay, pardon my abbreviation there. Unacceptable, poor, fair, good, excellent. Can you remember what type of categorical variable this would be? Is this a nominal or an ordinal variable? Remember, do these categories have some sort of natural arrangement or order? Since they do, this is a type of ordinal variable. So just a little review there. So we've got our variable listed here, and we need to, on the vertical axis, state how often each of those categories was observed, how frequently they happened. So we usually label the vertical axis as frequency. And I've got a fictitious data set in mind, and I'm going to put some tick marks here to represent 10, 20, and 30. And I better label those 10, 20, and 30. So now I'm going to put some bars onto this bar chart. For the unacceptable category, let's just presume that 10 ratings occurred in the unacceptable category. For the poor category, let's say there were 20, so I'm going to draw a bar up to 20. It's kind of leaning. Maybe I could try that again. There we go. For the fair category, I'm going to go all the way up to 30. And similarly with the good category, 30 ratings that were good. And in the excellent, let's do another 10. Excellent. This is a bar chart. It is a type of frequency distribution. It shows how often each of the values occurred in a data set. And in this case, the values are the categories. So, pretty cool. So in this bar chart, something to notice about the bars is that the bars do not touch. Bars do not touch. Sweet. We can also display the same information in a tabular format. So graphs are really nice, but sometimes a table is also desirable for certain reasons. We're going to create a frequency distribution table. It's going to display all the same information, but just in a table. I've already got one kind of queued up here. I do need to still have my variable listed. So I've got teacher rating right there. And I'm going to need the frequencies, how often each of those categories was observed. I'm going to go ahead and transcribe all these categories. And also the frequencies. And you might notice I've got a third column here. I've got a little foresight in the mix. I'm not going to use that right now, but I will in just several minutes. Okay, well, here we go. These two columns here are a frequency distribution table. Another element that is typically present in these tables is a total number for the frequencies. So if you add up the frequencies, you can see this is a very cookbook example. They add up to 100. And so that would be the sample size. And we've got a letter to represent sample size. That's the letter N. Go ahead and label that sample size. Cool. Well, let's go ahead and populate this third column, which is going to be about relative frequency, which is another way of saying the percent or proportion of observations that was observed in each category. Now I'm going to dish out a formula here, but before I do so, I want to see if we can actually figure out these relative frequencies without the formula in our face. Can we intuitively figure these out? And I'm also going to put those over here into our table. Okay, so the proportion of observations in each category. Well, we know that there was 100 total observations. Let's start with unacceptable. Wasn't there 10 unacceptable ratings out of 100? The relative frequency, therefore, for the unacceptable category would be, you can write this in all sorts of ways. I'll start with 10 out of 100. If you prefer a decimal, that would be 0.1. That's the same number, equals. If you prefer a percent symbol, make sure you know how percent works. Don't use percent if you don't know how it works. 10%. What proportion would be in the poor category? Well, wouldn't that be double the unacceptable? Because that is 20 out of 100, or 0.2, or 20%. And the trend continues. For the fair category, we've got 0.3, 0.3 again for good, and excellent, 0.1. Awesome. We better see how this formula can be written in general. We've just computed these relative frequencies for this specific example, but what would be a general formula for this? Notice there's a little division happening. The number in the denominator is always 100, but 100 was the sample size, which would be N And what's the number in the numerator? Oh, those are the frequencies. So I'll just write frequency over n. And there is a nice little formula for relative frequency. One more element about this table. Now that it has relative frequency, I suppose we could call this a relative frequency distribution table. It's a mouthful. Can you add up all of these relative frequencies? What do they add up to? They better add up to 1 or 100%. Those are the same number. I will write that here, that the relative frequencies must sum to 1. Awesome. There are other ways to organize categorical data. For instance, we could have drawn a pie chart, and we could have had different slices of the pie represent the different categories, and that would be great. We're not going to do a lot of pie charts in our class, but I'm sure you've probably seen them. They're very popular graphic in popular media. We're going to move on now to discuss quantitative data. And how do we organize information from a quantitative variable? It's a little different because recall quantitative variables are measured or counted. And so a data set's going to have a lot more unique values, usually if it's quantitative, than if it were categorical. Let's look at an example. In this example, we're going to look at heart rate in beats per minute of college students after spending 10 minutes on a treadmill. And I'm going to lay out an example of a frequency distribution table for a fictitious data set, and we'll see how it's a bit different for quantitative data. And then we will create the corresponding graph that would match the table. Now up here I say that frequency distributions for quantitative data are organized in classes or bins. Here there's going to be 6 bins or classes. And my first class is going to be a range of heart rates from 75 to 99 beats per minute. And let's just suppose there were 2 individuals who had this amazing heart rate after 10 minutes hoofing it on the treadmill. So that's one example of a class. This next class is going to start at 100 and go up to 124. And let's suppose there were 3 people in that class. You can maybe start to see a pattern. Do you know when my third class, where its lower bound is going to start? 125. We wouldn't want it starting at 124 because then there would be overlap between the classes. Can you tell where this class is going to have an upper bound? 149. And we got a few more to do here. 150 to 174, 175 to 199, and our last class here is going to start at 200, and we're going to break the trend here. You would think, oh, 224. Well, actually, usually we kind of like to close the deal nice and round, as some people say. This is going to be 225. So this is sort of an exception to the rule right here. A little exception. I'm going to go ahead and fill in the rest of these frequencies. I kind of got lost there. 8, 7, 4, 1. There are 6 classes or 6 bins. Each of these is representing a class or a bin. Now, like we saw in the previous example of a table, if we add up all of these frequencies, we will get the sample size. In this case, our sample size n is 25. There's lots of ways that I could have created these classes. I chose these classes in particular because we often like to have the classes start on, quote, nice numbers. So 75, 100, 125, those are, most people consider those kind of nice numbers to deal with. But we could have created these differently. Maybe I wanted not 6 classes, but maybe I wanted 5 classes. If that was the case, then each class would have to be a little wider. What is the class width currently? Well, how many beats per minute is this class spanning? It's 25 beats per minute, excluding the exception. Cool. Let's now transcribe this info into a type of graph. We're going to describe a histogram. Rhymes with your favorite social media. This is a type of graph that is used to organize quantitative data. It's got a ton of similarities to the bar chart, but it does have some distinct differences. We're going to lay down a set of axes, just like before. It's a little crooked there. That's a little better. And just like before, I'm going to label my axes as frequency on the vertical, and then my variable down here, which was our heart rate. I need some space. Let's do heart rate beats per minute. Beats per minute is the unit of measure there. Don't want to forget that. The smallest value of our variable possible is a 75. So that's where I'm going to start my tick marks. And each tick mark is going to be the start of a new class. So I'm going to put tick marks at 75, 100, 125, 150. You see the trend. And these should be equidistant. Since each class has a width of 25, each of these tick marks should be the same distance apart. My frequencies I have all the way up to 8, so I will go ahead and put tick marks all the way up to 8. And perhaps I should use one of those little chicka-chickas right there, a little break, since this distance from 0 to 75 is not very representative. Okay, let's go and create this histogram. It's going to have bars just like a bar graph, but let's see the difference. So 75 needs to go up to frequency of 2. That should do it. The next class, starting at 100, needs to go up to 3. Here's the difference. That bar is going to touch. So the bars do touch here. This next class needs to go all the way up to 8. And then 7, 4, 1. There is our beautiful looking histogram. Let's annotate some of the elements on here. Well, we did mention that the bars do touch. Yes, yes. Here we've got the peak. There is a special name for that, but we're not quite there yet. To the left of that peak, we would call this the left tail. Can you guess what this side is called? You got it. Presumably the right tail. Both the frequency distribution table and the histogram summarize and organize a lot of information of raw data. The raw data would be the 25 possibly unique heart rates that were all measured. Right? Imagine just a list of 25 numbers separated by commas. Right? That's a lot to look at to discern any trends. But when that is organized in a table, you can kind of see pretty quickly, oh, well, what appears to be the most common heart rate class? And that's very visible here in this image, the histogram. I mentioned earlier that we could have used fewer classes, maybe only 5 classes. That would have resulted most likely in a wider class width. I chose 6 sort of arbitrarily, but I did like the way it worked out with having these nice class boundaries, 75, 100, 125. What we will see, especially in lab, it's a lot easier with the computer software to create graphs really, really quick. What we are going to see is that the number of bars or bins or classes, whatever you want to call those, the number that you choose to use will dramatically affect the way that this data appears, what we would say its distribution. And it's not necessarily lying or being manipulative, but you can alter the appearance of a data set by choosing to display it in a certain way. And there's really no hard and fast rule about that, but we do have sort of a guideline to get you into the ballpark. A good starting point for how many classes should I use? Well, our sample size was 25. I wouldn't want 25 classes. That wouldn't summarize the data in any way. I wouldn't want 1 class, because again, that doesn't summarize the data. The number of bins or bars or classes is going to be not the sample size, but the square root of the sample size. And that should get you kind of in a nice zone for a decent looking histogram. And you'll notice, well, what's the square root of 25? 5, of course. Now, I broke my own rule, didn't I? Because I had 6 classes. Again, it's not a strict rule, but that should get you in the ballpark, maybe plus or minus 1 or 2 bins. On the topic of distributions, sometimes the shape of these distributions take on a particular characteristic. This histogram, for instance, you might even have a name for it already that you've heard about. Sometimes people would call this a bell-shaped distribution. And we're going to talk about some other shapes right now. So bell-shaped, that's the classic that I think a lot of people learn very early on. And it's a lot of times a little easier to draw this as a smooth curve, but as a histogram, a bell-shaped distribution is symmetric. There is a defined peak in the middle, and the tails descend on and on in a nearly symmetrical fashion. If you could imagine sort of smoothing out that that histogram, now it looks like a continual, smooth, symmetric, bell-shaped curve. A couple other common shapes that data sets take on are what are called right or left skewed. And as a histogram, a right skewed distribution is going to have a longer right tail. So the way this often looks is there is a defined peak over here towards the left, and then this right tail extends on and on. So a right skewed distribution, the right tail is longer. Right tail is longer. If we were to draw this in a more smooth curve sort of fashion, I would draw a peak over here on the left and then extend that right tail out. And I'm being a little sloppy with my labeling here. This should be the name of your variable. I guess in general I could call it y, and we would have a vertical axis here labeled frequency, but hopefully this gets the point across. With a left skewed distribution, you can imagine, well, that is when the left tail is longer. So there's going to be a peak towards the right and a tail that is descending towards the left. Left skewed. And if I was to draw that, that's good enough. A peak towards the right with a long left tail. Let's talk about a couple other not uncommon shapes for distributions. A uniform distribution. If you think about a uniform, like maybe a school uniform for attire, right? Everyone is wearing the same thing. With a uniform distribution, this is when all the frequencies, so maybe this will be better for me if I label this as frequency on the y-axis. This is when all the frequencies are roughly the same across the variable. And it doesn't have to be exactly the same, but it is mostly like a flat top here. So I'll label that y. So across the variable y, the frequencies are almost all the same. If I was to draw this as a smooth curve, sometimes this is kind of hard. This is just a flat top. Uniform. The last one I will touch on is a bimodal distribution. And this can occur in so many ways that I'm not going to draw a histogram example here. But bimodal, what does the prefix bi remind you of? Two, hopefully. And so this is when there are two distinct peaks in your variable. And sometimes the way I think about this is this could be how the variable naturally occurs, but sometimes this could be an indication that there are two elements going on in your variable. Like maybe, for instance, if you were looking at size of an organism, and here maybe the size was smaller for some group of that organism. I'll do it kind of in bluish here. Maybe those were the females. And then in pink, maybe this was another group of that organism, maybe like the males. And they got lumped together. So here you kind of see there's almost like two bells smashed together. And if two distinct types are grouped together, that can manifest in a bimodal distribution. That's not always going to happen. Maybe these would be indistinguishable, but that's one way that that can occur. It's kind of cool. One last shape, this time this is really the last shape that I would like to talk about, does not actually have a name, because the distribution of a data set doesn't necessarily have to fall on one of these nice little shapes. You can have a data set that doesn't really have a name, and when it's graphed up, I don't know what you would call that, the Fitzroy distribution, but this doesn't really have a name. It wouldn't fall in one of those categories. So not all data sets are going to be so textbook beautiful. It might defy description. Okay, well that's going to sum it up for this video. Hopefully it was cool for you. We've talked about different distribution shapes, histograms, and frequency distribution tables for both categorical and quantitative data, relative frequency, and bar charts. So it was a good time. See you in the next video.